Okay, so you type something into a chatbot and hit enter. But have you ever really stopped to think about what happens in that split second? How does it go from your words to, well, its thoughts? We're going to pull back the curtain on that very first, and maybe the most crucial step in how an AI actually learns to read.
I mean, think about it. You type a sentence and a chatbot just gets it. It understands you. But how? How does our rich, messy, kind of beautiful human language get turned into the cold, hard logic of a computer? That's the big mystery we're going to solve today.
Okay, so this right here, this is the whole challenge in a nutshell. On one side, you've got our sentence, let's do tokenization. On the other, that's what the AI actually sees, a string of numbers. See, at their core, these models don't get words at all. They only understand numbers. So there has to be some kind of translation step, right? A bridge between our world and theirs.
Well, that bridge has a name. It's called a tokenizer, and its entire job, its whole purpose in life, is to be that translator. It takes our text and turns it into the numerical data that a model can actually work with. So how do you build one? Let's check out the options.
So the first idea you'd probably come up with is, the most obvious one. Let's just make a giant dictionary for the entire language. Give every single word its own unique number, its own ID. Simple enough? Makes sense, right?
And yeah, it's super straightforward. You take a sentence, chop it up into words and punctuation, and then you just look up each piece in your massive dictionary to get its ID number. Boom. Simple, clean, easy to grasp. But, and this is a big but, that simplicity is hiding some really major problems.
For starters, just the size of it. To cover the entire English language, you need a vocabulary with over 500,000 unique words or tokens. That is just wildly inefficient for any computer model to handle. And believe me, the problems do not stop there.
So yeah, this method just falls apart on so many levels. First off, the model would see run and running as two totally separate, completely unrelated things, just different numbers in a list. Even worse, any word that's not in that gigantic dictionary, say a typo or some new slang, it just gets labeled as an unknown token. Get to many of those, and the AI is basically trying to read a sentence that's full of holes. The bottom line here, this simple approach, it's just way too fragile. It's not going to work.
Okay, so if a dictionary of 500,000 words is way too big, what's the next logical move? Well, we swing the pendulum all the way to the other extreme. What if we break everything down to its smallest possible part? We're talking individual letters, the alphabet.
So with this method, our sentence, let's do tokenization, suddenly becomes this much, much longer sequence of individual characters. L, E, T, apostrophe, S, space, and so on. We've definitely solved one of our problems, that's for sure. And look, the pros here are pretty great. Our vocabulary is suddenly tiny, just the alphabet and a few symbols. And poof, no more unknown tokens because you can build any word out of characters. But we've just traded one set of problems for another. A single letter, like L, carries way less meaning by itself than the word let's. And look how long that sequence gets. Now we're asking the AI to process this super long string of tiny, less meaningful pieces. That's also super inefficient. It's like we swung way too far in the other direction. So if word level is too big and character level is too small and meaningless, is there a just right, a Goldilocks solution? Oh, absolutely. And now we've arrived at the technique that pretty much all modern AI models actually use. It's this really elegant solution called subword tokenization. And here's the core idea. It is so brilliant because it's so simple. The principle is this. Really common words like the or and, they can just stay as single tokens. But rarer, more complex words, they get broken down into smaller, meaningful subwords. And just like that, we get the best of both worlds. Let me give you a perfect example. The word annoying. That's probably common enough to be its own token, right? And the suffix "ly," which you stick on the end of words, that's also super common. So when the tokenizer sees a rare word like annoyingly, it doesn't freak out and call it unknown. No, it does something smart. It just splits it into annoying and ly. Now the model can totally grasp the meaning, even if it's never seen that specific word before. It's genius. And hey, let's bring it all the way back to our first example. The word tokenization gets broken down into token and ization. So the model understands the root concept,
token, and it understands that the suffix ization usually means some kind of process or action. See? It's actually capturing the meaning, not just memorizing words. This is just so much smarter. So, this is it. This is the solution that checks all the boxes. We get a vocabulary that's a manageable size, we get fantastic coverage for new or rare words, and we basically get rid of those awful information-destroying unknown tokens. It really is the best of both worlds. All right, so now that we get how it works, let's kind of zoom out and look at the whole round trip, from your text into the AI's brain and then back out again as a response that you can actually read. That first leg of the journey, the part where your text goes into the AI's brain, that's called encoding, and it's a super quick two-step process that happens in a flash. Step 1 is the tokenization we've been talking about, right? Splitting the text into those smart subword tokens. Then, step 2 is just converting those tokens into their final numeric IDs from the vocabulary list. That final list of numbers, that's what actually gets fed into the AI model. Okay, so once the AI has done its thing with all those numbers and it's generated a response, it has to translate it back for us humans. That whole reverse process, it's called decoding. It's all about turning the model's number-based output back into words we can actually understand. And it's not just a simple reverse lookup either. The decoder is actually pretty smart. It's clever enough to reassemble all those little pieces. It knows that the tokens for token and ization should be stuck back together to make one word. This is what makes sure the AI's response is a clean, coherent sentence, and not just a jumbled mess of word parts. So there you have it. That's the elegant, clever bridge between our words and an AI's thoughts. This whole translation from our complex language into simple numbers, it's the bedrock that everything else in AI is built on. Which really leaves us with a pretty fascinating question, doesn't it? If our language can just be broken down into data like this, what's next? What other worlds of understanding are we going to teach machines to translate? Definitely something to think about.